Okay, the idea of mutually exclusive events that occur means that there are two events within the same sample space if they have no outcomes in common. So, for example, if you're rolling dice and an outcome of 6 has really nothing to do with getting an outcome of 9, there's nothing in common between them. Uh, in the terminology of sets, the intersection of A and B as the empty set would be the reflection of mutually exclusive events. So, in other words, if I look at this formula or this equation, okay, that says the probability of A intersecting B, there's no chance that there's an intersection or an overlap between these two outcomes is zero. There's no probability. And just from a terminology perspective, then upside down U means intersect, and that means union. Okay, so intersection would be the overlap, union would be the sum, putting everything together. If we're looking to find the probability of one or the other of two mutually exclusive events occurring, then we just add their individual probabilities. So, for example, if we're interested in the probability of rolling a 6 on a pair of die, well, I can get 6 by having a 1 and a 5, a 2 and a 4, a 3 and a 3, um, a 4 and then a 2, or a 5 and then a 1. Okay, and these are the possible outcomes that I'm interested in. There are 5 of them, and there are um, 2 to 6 outcomes possible for each die roll, right? So each time I roll, I'm rolling 2 die. The first one there's 6 possibilities. The second one there's also 6 possibilities. 6 times 6 is 36. So our probability is 5 out of 36 of rolling a 6. Um, the probability of rolling a 9, let's change colors here, um, that would have to be a 3 and a 6, a 4 and a 5, a 6 and a 3, and then a 5 and a 4. So it would be 4 out of 36. This would be for rolling a 9. This would be for rolling a total of 6. And if I'm interested in the probability of one or the other, I'm rolling 2 dice, and I'm interested in what are the odds that I'm going to get either a 6 or a 9, I add these two probabilities. So I'd take 5/36 plus 4/36, and I'd get 9/36, and I can reduce that to 1/4. Okay. Uh, so if A and B are events in the same sample space, just like we've been looking at, the probability of A or B occurring is equal to this, okay, which is what we just looked at. It's the probability of the two events added together minus the probability of the intersection of the two events. And this will make sense when we look at the next example. If they're mutually exclusive, we can leave off this last little piece here. Okay, and notice that it's just the probability of A plus the probability of B, which is what we just did with the dice coming up 6 or 9. Okay. So let's take a look at this one. We're taking a deck of cards, and you're selecting one card from the deck. We want to know that the probability that the card is either a heart or a face card. So our sample space is the same. It's simply the 52 cards in the deck. But there's two different outcomes that we're interested in. And if we look at this, um, the number of hearts, okay, we've got 1 through 10, or ace through 10, and then jack, queen, and king. So we've got 13 out of the 52 cards are hearts. If we look at the face cards, okay, face cards meaning jack, queen, or king, okay, there are 12 face cards, right? There's 3 jack, queen, king for each of the 4 suits, so it's 12 face cards. And then we have this overlap, okay? So if we define an outcome of A of being the suit and B being a face card, our overlap would be A intersection of B is the number of cards here in the middle, and that's going to be 3. Okay, so the probability that we have a heart or a face card is going to be the probability of a heart. Okay, well, actually, I'm going to call it P of A because I defined it as A, plus the probability of a face card, which is probability of B, minus the probability of the intersection. So let's look at these probabilities. We know that there are 52 possible outcomes. So the probability of A is 13 out of 52. Probability of B is 12 out of 52. And the probability of the intersection is 3 out of 52. And if we add all this up, 13 plus 12 is 25, minus 3 is 22. So this is 22 out of 52 is our probability. And if you want to know that as a decimal, it's about 0.423. So that would be our probability of A or B, heart or face cards. Independent events, meaning that one has no effect on the other. If you're flipping a coin, you flip it first, you get heads. It has no bearing on what the next flip is going to be. Even if you have a streak of 50 heads in a row, that 51st toss still has as much chance of being a tail as it does a head. Okay? So if we have independent events, and we're interested in finding the probability that two independent events will occur, for example, heads and then heads again, we multiply the probabilities together. Okay, so if we're interested in flipping a coin, the probability that it's going to be heads is 0.5, 50-50. Okay. The probability that it's going to land on heads and then heads again is going to be 0.5 times 0.5, which is 0.25. Okay, so we just multiply the probabilities together. Okay, so now we have a random number generator on a computer, and it is producing numbers between 1 and 20. And we're interested in finding out the probability that all three numbers, it's going to pick three, all three of them are less than or equal to 5. Okay, so these are independent events. Okay, and one does not influence the other. So the probability that we are less than 5 on any given random number generation, well, less than 5 means you could have the number 1, 2, 3, or 4, or 5, because it could be equal to 5. So it's 5 numbers out of a possible 20 numbers. So it's going to be 5 out of 20, which is the same as 1/4. Okay. Now we have 3 selections, so our probability that we have less than 5, less than 5, and less than 5, however you want to write that, is going to be 1/4 times 1/4 times 1/4, okay, or 1/64. Okay. Another way of writing this, we could say 1/4 cubed. Okay. But that's our probability. Okay. So in 2000, about 65% of the population in the United States was 25 years or older, with choosing 10 people at random, and we want to know the probability that all 10 were 25 years old or older. Okay, so the probability, given any one selection, the probability that we choose somebody who is 25 years or older is going to be 65%, or the probability of older than 25 is 65%, or 0.65. Okay. So we're choosing 10 of them, so we're going to have to multiply this, okay, 0.65 10 times, which I'm going to shortcut and do that. Okay. That would give us the probability that they are all 25 years old or older. And I don't have that handy. I'm just going to see if I can launch the calculator. Let's see if this works. See, my calculator is a little messed up. It is not working. Not sure what's going on there. Okay, so we'd have to multiply 0.65 to the 10th, whatever that is. Do that on the calculator, and that is going to give you your answer. Sorry, I don't have that for you. Another way of doing this is to say, well, or another way of looking at this is say, let's look at how many people are under 25. Well, if it's 65% over 25, then it is 35% or under 25. And let's just say that this comes out to be a number like, I don't know, 0.14 as your probability. I'm making that up. It's not, has nothing to do with this, but I'm just making it up. The probability that somebody is going to be under 25 is the complement of the probability that they're over 25, right? They have to be one or the other. So we could express this probability. We could say it's 1 minus 0.14, okay, which would be 0.86 would be our probability of the complement.